Hi, my name is Changjun. I'm a fourth-year mechanical engineering student at Georgia Tech, taking a course on design and manufacturing, and I'm here to discuss about my top 5 topics that I've learned and discussed in this class. So the first topic is casting manufacturing. So what is casting manufacturing? It is a casting process that involves the introduction of molten metal into a mold cavity where, upon solidification, the metal takes shape of the cavity. This workpiece will then undergo processing, cleaning, and any other necessary treatments. Applications of casting manufacturing include the automotive industry, as this process is used to make engine blocks, cylinder heads, transmission cases, and any other essential parts. The chemical processing equipments, they're also manufactured this way, such as reactors, heat exchangers, and pumps. Plant machinery parts are also manufactured in this process and include impellers, casings, and valves. For its importance, it is versatile, easy, reliable, efficient, precise, and overall a cost-effective manufacturing method. Some of the materials that are used in casting manufacturing include magnesium for aerospace and automotive applications, as it is lightweight and durable. Aluminum is used everywhere from automotive to consumer goods because of its high thermal conductivity, mechanical properties, and corrosion resistance. Lead alloys are used in areas such as battery manufacturing and radiation shielding because of its low melting point and malleability. For its capabilities, casting can be used to manufacture a wide variety of parts, from parts with cavities, thin hollow tubes, thin hollow shapes, tubular shapes, to super long detailed features, and very large and small parts. It is also very adaptive and include a wide variety of casting processes, such as sand casting, permanent mold casting, investment casting, and sludge casting. Its ability to create complex shapes and geometries that are not achievable with methods such as machining or forging is another one of its capabilities. For its limitations, the equipment and tool used for the casting process needs to be powerful and durable, thus requires a high initial investment. Casting is mainly used for metals with lower melting points, so there isn't really a great variety of materials to choose from. Potential shrinkage during the solidification process may lead to dimensional inaccuracies and the need for additional surface finishes. And that concludes the casting manufacturing topic, and now to my second topic, finishing manufacturing. So finishing manufacturing is the process that ranges from cleaning and etching to planting and chemical or electrochemical conversions. During these surface preparations, the workpieces are cleaned to remove greases, oils, and oxides. Solvents or detergents are also used before the workpiece is dipped in acid to further remove materials. Plating helps improve the adhesion of the material, and overall post-treatments help improve the product's properties and appearance. Industries that commonly utilize the finishing process include jewelry, automotive, aerospace, electronics, and fitness equipment. As for its importance, without the finishing process, the lifespan of parts and products can be reduced due to corrosion and wear, which can then lead to a diminishment of their functions. Finishing can also help achieve a product's or parts a range of desired characteristics, such as hardness, electrical properties, chemical properties, and the bonding of adhesives and coatings. For its capabilities, there are various types of finishing processes, each offering unique benefits mentioned previously. These finishing processes may include electroplating, abrasive blasting, hot blackening, and powder coating. Finishing manufacturing creates environmental and eco-friendly options as dry tumbling and dry blasting reduces the need for cutting fluids or chemicals. Additionally, in sandblasting, recyclable abrasive media are also commonly used. Finishing manufacturing also creates corrosion resistance and protection, as the coating process creates a protective layer against environmental factors. As for its limitations, it adds cost to the manufacturing process, it increases production time, it has potential for environmental impact due to waste material, there's a overall risk of overfinishing and causing damage to the surface, and there are limited applicabilities for some materials and geometries. Now on to the third topic, the abrasive machining process. The abrasive machining process is a subtractive manufacturing process that uses hard particles, or abrasives, to shape, finish, or cut a workpiece. It employs grinding, honing, or lapping to achieve the desired surface finish or geometry. Some applications of abrasive machining include surgical equipments or instruments to aerospace components. Its importance include the capability of achieving extremely high tolerances and superior surface finishes. It can be applied to a wide range of materials. It has a low setup cost, making it an economical choice for small batch production runs, and abrasive machining encompasses diverse processes, each tailored to a specific application and material requirements, such as grinding, which is used for achieving tight tolerances and fine surface finishes, and uses materials such as metals, ceramics, and composites, or buffing, which is used in automotive and metalworking industries to smoothen or impart a high gloss or shine on a surface, and in such removes scratches, swirls, or other cosmetic issues from metals, plastics, and wood. Its capabilities include high precision and tight tolerances, superior surface finish and texture control, minimal thermal damage and residual stresses, as it generates less heat compared to conventional cutting, and the low heat input also minimizes the residual stresses. For its limitations, however, it can impact production throughput as it has a lower material removal rate compared to conventional machining methods. It has a limited lifespan and require regular replacement and can contribute to ongoing operational costs. There is a risk of introducing microscopic surface defects or residual stresses, which can potentially impact the product's performance and integrity. Next, to topic 4, which is PLCM, or Product Lifecycle Management. This topic is a process of managing a product's entire lifecycle from ideation to retirement. It involves a systematic approach to product development, manufacturing, distribution, and support. PLCM is crucial for companies looking to gain a competitive edge in the market by optimizing their product offerings and operations. Applications of PLCM include Coca-Cola, and when a new Coke product was introduced, it was met with heavy protest and did not experience much growth or maturity, and in less than 3 months after it was announced, Coca-Cola reverted back to its original recipe. Product lifecycle management is important as it involves the coordination of people, processes, data, and business systems to ensure that a product is developed, manufactured, and supported efficiently and effectively. It helps to optimize product development, reduce cost, and make better informed decisions. It is a crucial aspect of any successful business. It is a comprehensive approach to managing all aspects of a product's lifecycle and includes development, manufacturing, supply chain management, distribution, and customer service. It also ensures that every step of the product's journey is carefully planned and executed. As for its capabilities, it centralizes data management, and it serves as a central repository for all product-related data such as CAD files, bill of materials, and documentation. This way it ensures consistency and accessibility across the organization. It ensures sustainability as it can track materials, waste, energy consumption, and adherence to sustainability goals. It helps with global collaboration as it provides a platform for seamless global collaboration, allowing organizations to leverage expertise from around the world. As for its limitations, its inability to adapt quickly, as it has a rigid POM system, which leads to wasted time or costly workarounds. It may have incompatible files, which require exceptional admin work. The legacy systems and data may not really integrate well into the enterprise PLCM system. It has a high implementation cost as it requires a significant financial investment in software, hardware, and network infrastructure. Complexity and usability issues as it can be challenging to learn initially and may lead to resistance or slow adoption among employees. And lastly, topic 5, computer-aided process planning. Computer-aided process planning is the use of computer technology to aid in the process of planning for a product or part in manufacturing. It bridges the gap between product design and manufacturing, and applications of CAPP include the manufacturing process optimization, which helps in selecting and sequencing operations to optimize manufacturing routes, minimizing waste and production time. It helps with cost estimations and reduction, as it provides a detailed breakdown of labor, materials, and machine usage, enabling more accurate cost forecasting. Its importance include that it enables a more efficient, accurate, and flexible production process. It enhances consistency and standardization, promoting standardized methods and practices across manufacturing operations, and ensures that the product are manufactured to the same quality and specifications each time. It plays a role in cost reduction, improves quality control, and has a great competitive advantage. By streamlining the planning and production processes, CAPP enables faster production development and delivery. Its capabilities include quality control and assurance, standardization of processes, cost estimation and analysis, integration with CAD and CAM systems. For its limitations, however, it has a complex initial setup, as there is a high implementation cost due to costs associated with software, hardware, training, and maintenance. It is dependent on data accuracy, as it relies heavily on accurate input data, and if the data is on the machine's tools or materials is incorrect, It can lead to poor quality output and inefficient planning. It may sometimes be incompatible with legacy systems, as many traditional manufacturing systems and equipment may not be compatible with modern CAPP systems, limiting the benefits and making integration difficult. Here are the references I've used when researching and brainstorming these particular topics. Before I end this video, I would like to stress that I've completed this project based on the knowledge learned from the design and manufacturing course, and this was purely for educational purposes. Thank you for listening.